So we talked before about this thing called Noether's theorem, N-O-E, that's an E-T-H-E-R apostrophe S theorem, SS theorem, which is the theorem that states that whenever you have a symmetry, a continuous symmetry in your system, that you will have a conserved quantity that's associated with it. And we gave two examples already, and that was that if you have a time coordinate, if your time coordinate doesn't change, as you advance in time, if the space between your time coordinate, so like the second, doesn't change length over time, then you will have a conserved quantity called momentum. Of course, I said it wrong. You'll have a conserved quantity called energy. So energy is associated with the time coordinate. And then we also talked about when you have a coordinate system where the separation between successive marks in your coordinate system, if your coordinate system is invariant to translations in where the origin is located, then you will have a conserved quantity associated with each direction that has that property. And so that is called momentum. So it's momentum and distance, or like position. So momentum is a conserved quantity associated with the invariance in position from your coordinate system. If you have a coordinate system, and I've mentioned this before, where these things are not the same, they're not equidistant, so they get shorter or closer and closer together or farther apart, then momentum is not conserved in that direction. And the way that Einstein's gravity comes in and changes conservation of energy and momentum, it changes conservation of energy and momentum because in Einstein's general relativity, energy and momentum, the way they're traditionally defined, are not conserved quantities, because Einstein's theorem or Einstein's theory distorts space-time. It distorts the coordinate system in the spatial directions and in the time direction. And so there's no longer conserved momentum and conserved energy. Instead, there is a different structure that is conserved, a different quantity that's conserved, which is like the trace of the energy momentum tensor. I don't know the details of it, but there is something that is conserved, but it's a combination of all these things that's conserved that remains invariant, given the fact that the coordinate system has been distorted. But for classical physics, we choose a coordinate system that is invariant under translations. We choose a time measuring system that is invariant under translations in time. You can set the clock back an hour. Daylight savings time doesn't change the physics. And that gives us these conserved quantities, energy and momentum. And so these conserved quantities are useful because then you can formulate physical theories, or you can formulate your equations exploiting the fact that these things are conserved. Energy before is the same as energy after, and then you can set up, the before, like the beginning and the end state of your system. Question. Okay, so there's a question about CERN. I have visited CERN. I've given at least one talk there. I don't know if I've given two, but I've been to CERN a couple times. And yeah, they upgrade CERN. They upgrade these particle accelerators fairly often. So this is momentum. We talked about momentum, how we went into detail that momentum is conserved, and that's why when you have two objects that come and collide with each other, they will bounce off of each other and they will carry away that momentum. We've also talked about there are different forms of energy. Energy can come in potential and kinetic energy. The kinetic energy is related to the motion that an object has, and the potential energy is related to the position that the object has relative to a coordinate system where you have some ambient fields that can provide the energy. The coupling of those fields provides the energy, and those fields have values that depend upon the coordinates. And so you have potential energy that is related to your position in those coordinates relative to those fields. And the kinetic energy is just your motion in that system. With momentum, there's basically just one quantity of momentum, and that is the mass times the velocity. This is the quantity of motion that Newton, that's how he described it in his Principia. There is another set of symmetries that you can have in a system, and those symmetries are symmetries under rotation. You can say it doesn't matter, for example, suppose you have a ball that's moving through space like this, and you want to analyze its motion. You can analyze it with this coordinate system, and you'll get some relationship between the object's motion and your coordinate system. You could also choose this coordinate system that looks like this. So you can rotate your coordinate system some amount, and the physics of this ball is not going to change. And so if the physics of the system is invariant under rotations of your coordinate system, then there's going to be according to another theorem, there's going to be a conserved quantity associated with that rotation. And so how do you define a rotation? Because a rotation is actually messing up these two axes. You have to define a direction that's associated with that rotation that doesn't change when you rotate. And so that is the perpendicular direction here. So in this case, a rotation in this plane would be a rotation about this axis. And so that's the direction you assign your conserved quantity. You assign a conserved quantity in this direction that corresponds to the rotation axis that you're referring to. So you have some rotation in some direction. If physics is invariant under rotations in this direction, meaning that you can have either this coordinate system or this coordinate system and get the same result, then you have a conserved quantity, and that's called angular momentum. Angular momentum. So angular momentum would exist in the absence, your coordinate systems could be messed up. Like you could have coordinate systems where one axis is longer than the other axis, at which point it no longer is the same under rotations. And so the angular momentum would not be the same. So angular momentum is a mathematical quantity that you can define. And it turns out that if you have a coordinate system that has this symmetry where it doesn't matter the orientation of that coordinate system, the physics remains the same, then you get a conserved quantity. Then angular momentum is the conserved quantity that's associated with it. So there you go. So this is, that's where angular momentum, well, that's where conservation of angular momentum comes from. There is a quantity called angular momentum, and we choose coordinate systems such that this holds true, that it doesn't matter the orientation of your coordinate system as long as you're consistent. And so angular momentum as a consequence is conserved because of that. So because there are three different directions about which you can rotate, there are three different independently conserved angular momentum, one for each direction. And so you'll hear in physics classes people say, well, angular momentum is a vector. Okay, fine. It's a vector, meaning that you have three independently conserved angular momentum quantities that you can put in an arrangement that looks like angular momentum x, angular momentum y, and angular momentum z. So anyways, and this is, there you go, that's angular momentum. That's where it comes from. Then when you say angular momentum is conserved, it allows you to solve a variety of problems that have to do with rotations. A few things to point out about angular momentum. One of the things we talked about last time is that when you do this Lagrangian formulation, the formulation of mechanics or dynamics, how forces interact with different objects and how those objects how their motion will evolve as a consequence of those forces. We mentioned the fact that how did we describe it? We described it as you put that information into the Lagrangian. So you have this Lagrangian, which I don't remember if I used it with script L, or usually I write it with a script L, but I don't remember if I did or not. I think I just did it as regular L, which means that it's going to now collide with the fact that L is also the letter associated with angular momentum. But anyways, the Lagrangian is the potential energy, the kinetic energy, which was given by T, minus the potential energy, which is given by V. So this is Lagrangian. It tells you basically how much energy goes when you have a total amount of energy in a system, which would be the sum of the kinetic energy plus the potential energy. And this is kinetic. They didn't choose K because they didn't choose V because also that doesn't look like potential energy. But nevertheless, this is the standard notation for these things. So you have kinetic energy plus potential energy. This is the total energy, but this the total energy doesn't tell you how the energy is shared between the potential and the kinetic. The Lagrangian does tell you about how it's shared. It tells you if there's more potential energy than kinetic energy, then it will be negative. If instead there's more kinetic energy than potential energy, then it will be positive. So the Lagrangian tells you how energy is shared between these two different forms, and it allows you to then derive the motion of something based upon Lagrangian, how it behaves. So if you have, now we're actually looking at a thing where we have an angle or a coordinate with our system. So if we have, here's our original coordinate system that gives our x and y values of velocity or position. But now we have a new way of moving through space. We can take an object at a given distance and we can rotate it like this. So that rotation is going to have a new coordinate. I'll call it theta because that's what we always do. So now we have a new coordinate, but theta doesn't have units. So one might think that it has units of degrees, but that would be a lie because angles don't have units. It's a unitless ratio, which is the ratio of the distance here to the radius. So if this distance is s and that radius is r, then the angle here is s over r. So that by the time s goes through 2 pi, you've gone through, or s has gone through the circumference of a circle, then you get the ratio of s over r is 2 pi. So this doesn't have units of distance. Nevertheless, it's still a coordinate. And so there is going to be, and we've already mentioned that there's going to be quantities of motion related to these kinds of rotations, and there's going to be a momentum associated with that, an angular momentum associated with that. And so we're going to see that some of the equations that come up from linear momentum, motion in a coordinate system where you're moving in a line, it will translate to rotations, but there's going to be some weirdness with the units that are going to be, point to kind of deeper philosophical aspects of this. There's a question here. Let's say a planet orbit around the sun, the total momentum of the system is 0. A planet loses all orbital velocity, the total momentum is still 0, right? So if you have a planet like this with, here's a star and here's a planet going around it, your question depends upon like what you mean by momentum. So in this case, you have a planet going around a system. The system can have some momentum. That would be, here's the center of mass of the system. That center of mass might be moving with some velocity relative to your coordinate system. That will always be conserved. If the planet that will always be conserved provided that there's no external forces out here that are changing the properties of the system, changing the dynamics of the system. So if it's just the two things interacting with each other and sharing energy and sharing momentum somehow, well, sharing energy, then the total momentum of the system will be conserved. And so if this planet loses energy because of tidal interactions or friction or something like that and spirals in, the total momentum of the system will still be conserved. It will still be moving at a constant speed in a straight line because there's no outside forces acting on it. So what happens to the energy of the system? Well, initially there's some energy associated with the orbit of both the star and the planet. That energy gets dissipated somehow. We're ignoring the fact that the sun is shining. That's a separate source of energy. So if we're not counting the nuclear energy that is being converted into photons that are leaving, we're not worried about that. We're just worried about the mechanical energy of the kinetic energy of the different objects in the system. Then what's happening is, as it spirals in this case, it has to spiral in because of some kind of interaction. That interaction is presumably due to tides, which causes friction, causes the planets to distort their shape. That distortion is rocks grinding against each other, which causes the rocks to heat up. And so you basically are converting the kinetic energy of the orbit into the kinetic energy of the random motions of the particles in that system, of the planet and of the star. And so you're heating up the planet and the star and taking energy out of the kind of bulk motion of the object and converting it into the random motion of the particles that make it up. And that's where the energy gets lost. Still, the momentum, the motion that the whole system has relative to your coordinate system is going to be conserved. Let's see. Let's say the planet loses all orbital velocity, the total momentum. So the total linear momentum is still 0. The angular momentum, which we haven't gone into detail yet, but that's what we're talking about today, this also has some angular momentum associated with its orbit. And the reason it's going to lose angular momentum, the reason it loses angular momentum is because the same force, the same internal force that's acting here, which is the tidal force. Tidal force is a gravitational force. Basically what's going on is that the planet and the star distort each other's shape. So here is the star, here is the planet, and they both get distorted. The star it's easier to distort the star because it's a fluid, but anyways, here it is, gets distorted. These things have some rotation. So this one has an orbit. They also spin on their axes. And as long as these bulges don't line up with each other, so if these bulges don't line up with each other, because say the star spins faster than the planet orbits, which would imply that the planet that the planet, okay, what would that look like? So if the star spins faster than the planet orbits, then you'll get a situation that looks like this. The tide that's raised on the star, this is exaggerated, of course, the tide that's raised on the star will be pushed forward by the rotation of the star so that it leads the planet. It's out in front of the planet. And there you exert a torque, which we haven't talked about yet. You'll exert a torque on the planet, and that will cause the planet's orbit to change. So the angular momentum is still conserved. It just gets shared again among the spins of the objects and the orbits of the objects. So what can happen is, as this thing spirals inwards, it will lose angular momentum, and that angular momentum can be picked up by causing the star to increase its rotation rate. So all of these things still hold together. Okay, so in some frame, right. So this also goes back to what we discussed before. You have this planetary system that's moving with respect to your coordinate system. There exists some frame. You can boost yourself into a coordinate system where the center of mass is stationary, and this is your new origin. And that comes down to the fact that forces cause a change in velocity, but the velocity, the initial velocity and the initial position, are two things that you can choose for your coordinate system. So you can always take an arbitrary system and boost it to a coordinate system where there's no bulk linear momentum, where the velocity is something that you can pick so that the center of mass of the system stays fixed, and you can pick an origin that's handy dandy for solving the problem, because you get to choose an initial position and an initial velocity in your coordinate system. So the question here is, I don't know who that is. Question here is, what if a planet took external momentum to lose all v? If a planet takes external momentum and loses it that way, that's an external force, and so it's no longer part of the system. And once you have external stuff acting on your system, then momentum is no longer conserved. It's only conserved when you isolate your system and say, I'm only going to consider what's going on inside my system. Okay, so what we had before is that forces cause masses to accelerate, or forces cause changes in momentum. Remember that this P is momentum. Changes in momentum with respect to time. Forces cause a change in momentum. And now we're saying that we have a new momentum, a different momentum, that is, instead of being a translation, it's a momentum that's actually associated with a rotation. And so there's still a second law. There's still a forces, the equivalent to forces cause masses to accelerate, but now acceleration means a different thing. So before, acceleration meant accelerating in some particular direction. Now, when we're talking about rotations, an acceleration actually means expanding in whatever the new position coordinate is. But the position here is an angle and not an actual physical position relative to an origin. It's a physical orientation relative to an initial origin axis. And so there is going to be another Newton's second law, because all the same things apply to this system under rotations that applied to a system under translations, except now it's a different symmetry that's conserved, and so you get a different Lagrangian, and you get different behavior, or different relationship between your coordinate, theta, and your conserved quantity, angular momentum. So the way that that's written is that now, instead of a force, we call it a torque, and we usually we, the scientists, or we, the physics instructors, use tau to describe it. So you have a torque causes, now there's a different kind of mass. It's no longer this mass, because that's not the quantity of motion that is, angular momentum is a different quantity of motion. Linear momentum is this quantity, mass times velocity. Angular momentum, the equivalent of mass is actually called the moment of inertia, I. And it's how is the mass distributed around the rotation axis, not how is the mass distributed in your coordinate system. So how is a mass distributed around your rotation axis is this quantity I. So, but that's the equivalent of, that's mass under rotation, is this moment of inertia. So you get I, and then instead of an acceleration in a linear space, like a translation acceleration, we have a rotation acceleration, and that is alpha. Another way to do this is the torques cause. So instead of a linear momentum here, it's an angular momentum, dl dt. These are the two equivalent formulations of Newton's second law, but now we're talking about a rotation to a coordinate system instead of a translation in a coordinate system. And we have different ways of measuring position. So now instead of position having units of length, the position has the non-unit of angle. And instead of the mass having just this unit of mass, it's a mass as it's distributed around the rotation axis, which is a moment of inertia. And instead of a force, we have a force that is applied in a particular direction, and that's called a torque. Okay, everything else stays the same. So there's going to be some kinetic energy associated with a rotation because you have a mass quantity, and that mass quantity is going to be rotating with some angular velocity. And so with translational kinetic energy, we have 1/2 mv squared. With rotational kinetic energy, we're going to have 1/2, and it's going to be I. So m, the mass under rotation is a moment of inertia. And then instead of a velocity, it's given by omega, little omega squared. So all of this, it's spelled differently, but it's the same effect. And in the Lagrangian formulation, it's exactly the same thing. You have a coordinate that gives you some position in your coordinate system. You have a momentum associated with that coordinate, and those things are related to each other through an equation of motion. For the case of rectilinear motion, this is your equation of motion, F equals dp dt. And for a rotating system, the equation of motion is this. Torque is the change in angular momentum with respect to time. So fundamentally, they're the same thing. It's because it's a different way of describing the same physics. And angular momentum happens to be, not only is it a useful quantity, but it's a conserved quantity. This actually shows that it's a conserved quantity. If you want to change the linear momentum, you have to exert some external torque on it. If you want to change the angular momentum, hopefully I said the angular momentum, you have to exert a torque on it. From either if you want to change the angular momentum of a particular object within the system, you have to exert a torque on it from within the system. If you want to change the angular momentum of the whole system, you have to exert some external torque on it. And torque is the mechanism through which angular momentum is transferred from one thing to another. Okay, fundamentally, just like forces are related to the motion of, or like the forces interacting between different objects. So for example, if you say what's the tension in a rope, tension in a rope is a consequence of, here's a bunch of atoms in that rope. They're all bonded together with each other because of the interactions of the electrons in that system. And so when you pull on it, you're actually inducing stress in the rope, causing these bonds to, you're putting strain on the bonds, stressing the bonds, and those bonds prefer to stay together, and so it builds up this tension. You have the rope that's kind of pulling in on itself as you try to stretch it, and that's how the tension builds up in the rope. For the case, and fundamentally, momentum is transferred from one object to another through the electromagnetic interactions of the charged particles in that system. So if you have a spring force, again, it's these bonds. The bonds are between electrons, in a potential, electrons and protons in this structure, and those interactions, those all take place through the electromagnetic field. So tension in a rope is a force that emerges from the fundamental interactions, which is the electromagnetic interaction. So the electromagnetic interaction is the exchange of photons. We have photons that are being passed back and forth between the different particles in a rope, and it's that photon field that creates the tension in the rope that we experience as we pull on the tug of war. Photons also carry angular momentum with them. So when you're exerting a torque on something, so let's say that you have a wrench or something like that, and you have a string and you're pulling on the string, the angular momentum actually gets transferred from one object to another through the exchange of photons. And it fundamentally comes down to the fact that in this case, photons, they can have angular momentum with respect to some object. They can have like essentially orbital angular momentum, but photons also have spin. And so the photons carry spin with them. Spin has units of angular momentum. And you can have one object interacting through the electromagnetic force, which would be like a wrench in contact with the surface of your bolt or whatever. And the photons that are exchanged between the electrons in that system are what are actually causing this thing to turn. And that are actually changing the angular momentum of the system is fundamentally through the exchange of these particles that can have either angular momentum themselves relative to your coordinate system, or they can carry spin in that coordinate system. So that is pretty real. Do I mean real or virtual photons? So these are virtual photons that are exchanged between the particles, objects in that system. So here's your wrench. Here's the head of the bolt, and you have your wrench around it that looks kind of like this. And as these things interact with each other, they're exchanging electromagnetic impulses. The electromagnetic field is interacting between the two, and the fact that this thing is going to start accelerating because of this torque that is being exerted upon it, that angular momentum comes from the angular momentum properties of the photon and its spin properties. So, because angular momentum is conserved in the coordinate system that we choose, and so the angular momentum has to come from somewhere. And you can generate it through either orbital angular momentum or spin angular momentum. So there we go. Now that's pretty weird. The fact that when something spins, it actually fundamentally comes down to either the orbital angular momentum that something has or the spin angular momentum that something has. And spin is a quantum property. Orbits are a coordinate property. Because if you just have an object in a particular location, an orbit is defined by how is something circling around a particular axis. And so this object can have orbital angular momentum because it is spinning around a particular axis. But if you move the axis to the location of the object, then it no longer has that orbital angular momentum. So orbital angular momentum is a coordinate system dependent quantity. And that's because this quantity I, the moment of inertia, also depends upon the coordinate system. So might as well talk about what moment of inertia is. So the moment of inertia, I, is the microscopic version of it is, so I guess like a little bit of I, is a piece of mass and the distance that it is squared from your origin. So this is the distance squared from your origin. So if you have an origin here and you have some object that's out here, some distance r, and this has mass, then the moment of inertia of this object as it that would be rotating around this particular origin, that particular rotation axis, is going to be mr squared. So if you have a distribution of stuff, then you have to add up the contribution of all of these different things, at which point then you're talking about integrating this. So you're integrating a little bit of mass and wherever it happens to be located relative to your coordinate system. So if you have an object and you have a spinning coordinate system like this and your object is located at the origin, then this r goes to 0 and there's no moment of inertia. And so mr2, exactly. Okay, so this moment of inertia is the equivalent of mass, but again, it is, in this case, coordinate system dependent. It depends upon how you place your object relative to, for one thing, how you place your object relative to the rotation axis, and that rotation axis is typically where you would choose to have your origin. You could imagine having your coordinate system up here that is not, where the origin is not tied to the spin axis, but then it gets really messy really fast how you treat something like that. So it's sometimes you don't have any choice, but typically it's not recommended. Okay, so that is that tells you all these things and how they relate to momentum. So let's talk about the differences between like angular momentum and spin. So there's a thing, a quantity called quantum spin, and it happens to be a conserved quantum number. It has units of angular momentum, but it doesn't actually, this is just a euphemism for something that is fundamental and attached to the object. The object has spin the same way that an object might have electric charge. An electron has spin in the same way that it has electric charge. It is a quantum property that's essentially painted onto the surface of the electron. The electron has a spin. It doesn't actually imply that the electron itself is spinning. So if you have a hydrogen atom, so here's your proton like this, and you have an electron that's out here, the electron has quantum spin that has units of angular momentum and actually is kind of the fundamental unit of angular momentum. Here it has spin, and it also, because the electron is going around, or the probability density wave is going around the proton, it can have orbital angular momentum associated with the fact that it is displaced from the center of mass of the system. If the electron were located right in the center, then it would have zero angular momentum. And in fact, if you look at the shape of the orbitals of the electron in the there are a variety of different waves that the electron can fit around the nucleus, and there are some of those waves that are spherically symmetric and that have a maximum value at the center. And those ones, because they are symmetric about the center in all directions, have no angular momentum. There are two of them. There are two electrons with each of those things, one associated with spin up and one associated with spin down. Two electrons associated with those things that have zero angular momentum. The states that have zero angular momentum are the two columns on the leftmost side of the periodic table. So the periodic table looks like this. It has two columns right here, and then you've got 10, and then you've got 6 here, and then there's one that kind of sticks up there that actually kind of belongs over here, but it also kind of belongs over here. So helium belongs in two places at the same time. These two columns here are the states where there's no angular momentum for the electron in that state. And that's because the wave function that describes the probability of measuring this electron at any given location is centered at 0. Okay, and I mentioned before that if you're centered at 0, then the rotation doesn't matter, right? If you have your coordinate system like this and you put your object right here, then it's going to have there's no I at that thing. It's only when you set it out off to the side where you're going to be able to get some kind of angular momentum. So if I is 0, then the angular momentum, which is I omega, that's also going to be 0. So just like regular momentum is P. Regular momentum is P, and that's the mass times the velocity. The angular momentum, L, is now the rotational mass, I, times the velocity, which is this omega quantity. Okay, why is spin 2 dimensions and not 3 dimensions? Up, down, left, right, not forward and backward. So spin can be measured in all 3 dimensions because there are 3 different axes about which you can rotate. You can rotate about, well, because we live in 3 large spatial dimensions, you can rotate about each of those directions. You can rotate about any 3 directions because we have 3 directions to choose from. If we lived in a 4-dimensional space, then there would be 4 angular momenta that are conserved. Well, if you choose the coordinate system right, there would be 4 angular momenta that are conserved, and there would be 4 different axes about which you can rotate. So when you want to think about spin, yeah, the spin, an object might be rotating in some plane, and it's a 2-dimensional plane, but there's one direction associated with that plane, and that is the normal to that surface. And so, anyways, going back to what I was saying before, because the distribution of the particle is centered at 0, it's like having it at the origin, and so there's no angular momentum associated with it. So the 0 angular momentum states are in the periodic table are, what is it? P table. The halides and the something or others. So I think these are the halides, and then these are something else. They have a name associated with them. Anyways. What are they called? Alkaline earth metals. So alkaline metals and alkaline earth metals, which are different than alkaline metals by 1 electron. But these are the ones where the outermost electron has no orbital angular momentum. Okay, and the reason it has no orbital angular momentum is because the shape of the wave function is centered at what would presumably be the rotation axis that you're talking about. So that is pretty gnarly. That's pretty gnarly. Okay. Also pointed out is that the electrons themselves can have spin, but that is an intrinsic property that is not related to its configuration relative to your coordinate system. So you have spin angular momentum that's an intrinsic property, and you have orbital angular momentum that has to do with how the particles in the system are distributed around your origin, and how those particles then move with respect to that origin. Okay, let's take a look at some of the consequences of this spin. So what's a good example? So let me start here and present some of the stuff present the animations that I put together. And so let me briefly talk about, that's basically the material that's coming out of the book for today. What's going to happen next time, which will be Thursday, is that we're going to, now we've talked about the forces, we talked about the coordinate system, we talked about the conservation laws associated with the symmetries of our coordinate system, we talked about the quantities, so what those quantities are and how they're conserved, energy, momentum, angular momentum. And what we're going to do now is we're going to say, okay, what are these forces that we can have to develop potential energy? What are the forces that exist? So now we're going to go talk about the four forces of nature and how they, how those forces allow you to store energy in the field and then release that energy and put it into the motion of the different particles, how to slosh energy around between the potential energy associated with the field or the force and the kinetic energy that comes from the response of the object to those forces. And so the first force that we're going to talk about is gravity. And then we'll go on to look at some of the consequences of that. So gravity and angular velocity and the orbits of planets and things in the gravitational field, all of that is from one particular force. The next set of concepts that the book goes into, so we'll follow along with the book, is fluids and how fluids work. And fluids is basically exactly the same stuff, except now you're talking about the bulk properties of the movement, the bulk movement of individual particles, instead of the random movement of individual particles. Well, it's a combination of separating the random movement of individual particles with the bulk movement of those same individual particles. And for the case of fluids, you do it, it's all exactly the same stuff that we've done in terms of coordinate systems and momentum and energy, except now we're also adding to the system gravity, and basically fluids is all the same stuff except now with kind of a continuous medium that is composed of a bunch of small particles. And then, so we go through all of this stuff, heat and energy transfer, thermodynamics. This is all kinetic energy, potential energy. There's no new forces here. They just add gravity into the mix because then you can get Bernoulli's equation. It's not until we're going to get quite a bit later here, chapter whatever this is, 18, where we've now gone beyond kinematics, kind of bulk forces, gravity, and now we look at the electromagnetic field and what are the consequences of the electromagnetic field. And that takes a bunch of time. And really, after that, this is all electromagnetic field. The second third of the book is electromagnetic field. And then we do the other forces of nature at the very end. And we don't spend much time on it at all. But those are the interesting ones. I mean, all the forces are equally interesting but they're all interesting in their own way. I mean, maybe some are more equally interesting than others, but anyways, each force has its own unique personality. Gravity is the next one we're going to add to the mix, and then we'll go on with what are the consequences of gravity and what are the consequences of the atomic nature of matter. The fact that matter is not, a baseball is more than just a baseball. It's the sum of all the parts of the baseball. We have four forces: electromagnetism, gravity, the strong nuclear force, and the weak nuclear force. And you can count them that way, or you can count them the way that the Europeans do, or at least the French do: electromagnetism, gravity, strong nuclear force, and weak nuclear force. All right, so let's talk about spin for a moment. One of the things that comes up frequently with spin is the fact, let me actually pull up my animations before I forget. So it's going to be here. So here's the situation. Physicists and astronomers, we say that, and physicists do it, astronomers just go along for the ride. Physicists say, particles have intrinsic spin, and it's a quantum number associated with that thing, and fundamentally what it's related to is how the phase of the quantum wave function advances as you rotate your coordinate system. So the way that this shows up in an equation is you're going to have a quantum mechanical wave function. It's going to have a factor in it. That factor is going to have an exponential. There's going to be an I in there because that's how you get things to rotate. And it's going to have some angle. That's an angle that's related to how the object is rotated, or how that can rotate the coordinate system. And then it's going to have a spin in here, your spin. And the quantum number associated with your spin is, that's the spin. Most particles that we think of, electrons and things like that, have a spin equal to 1/2. And there's an h bar in there, but we're going to ignore that for the moment. We're going to use the units where h bar is equal to 1. So most particles that we think of will have a spin 1/2. Those are electrons and protons and neutrons and things of that nature. There are other particles that have different spins. Photons have a spin of 1. Gravitons, like if gravity is actually a quantum phenomenon, and then you would have a particle associated with the gravitational field that's the equivalent to the photon. That's going to have, the graviton is going to have a spin of 2. You can also have particles that have a spin of 0. So the Higgs particle, it's called a scalar, and that has a spin of 0. So what do these things look like? What does it mean for something to have a particle, or a particle to have a spin 1/2, or a spin 1, or a spin 2? What this implies, if we take, for example, the spin 1/2 and we put it into this, we have e to the I theta over 2. Okay, and then one may recall that whenever you have an exponential with a complex argument, this actually corresponds to sine theta. Let's see, it's cosine theta. Cosine theta plus I times sine of theta. Okay, so an exponential of a complex number gives you oscillations. And just like if you take an oscillation, like a cosine function that oscillates, and you put in a complex number, then you get an exponential. So these two things are related to each other, and it's related. This is a portion, it's a factor in the quantum wave function, is this spin phase. So what this implies is that when you go through a rotation, when you go through a rotation in phase, so you go through a full 2 pi rotation, rotation in phase, you don't actually go through a full 2 pi rotation of the wave function. And that's a little bit weird. Like I rotate something and it doesn't rotate the amount that I think that it should. And so what I have is a set of animations that outline or kind of demonstrate how you can have a system where when you do a complete rotation in your coordinate frame, it doesn't correspond to a complete rotation of the system. So this is an example. A scalar particle is a particle where there is there's no spin associated with it. It's got 0 spin. Another example of a scalar field, so we have the Higgs as a scalar field, but temperature is another example of a scalar field. It's just a number at some location. There's no direction associated with it. It just has values that are located in one place or another. So what I'm showing here is as this animation plays, the top frame is going to rotate. It's actually rotating the coordinate system, but instead of rotating the coordinate system, I'm going to rotate the object within that coordinate system. So this thing is going to rotate, and if I click the right buttons, it will rotate continuously. And you'll see the phase of the rotation of this object relative to this coordinate system. The bottom arrow right here, this corresponds to the normal to the surface. So this is a top view, this is a side view, and this thing is going to rotate. This ring is going to rotate. And this arrow here corresponds to the normal to that surface. So here is that surface, that rotating surface. It's going to be the piece that's sticking like straight out as though it's attached to that surface. So here we go. I need to do what? I need to go, I think it's this combination of points, and then I go like that. So you'll notice that the top thing is spinning around. You can see that it's spinning around because of the amazing animationness of the bottom frame. But you'll also notice that the normal to this surface doesn't change. And so it stays fixed at whatever value it happens to have. Like the direction stays fixed. So even though you're rotating this thing by 360 degrees, the bottom one doesn't rotate at all. It has no spin. There's no coupling between the rotation of the coordinate system and the orientation of this surface. So this is an example of how something can have, how you can rotate a coordinate system and you have no spin. There's no response as a consequence of that. Okay, now let me give you an example of something that has unit spin. So what I did to produce this, let me let's try it. Here we go, this time for sure. All right, here we go. So let me go to this camera. All right, so this is a thing. This is a thing. And it's going to be eventually folded or rotated around so that it now is coupled to itself, which means that as I rotate, if I rotate 360 degrees around, I get back where I started. Okay, and I want to couple to this. I want to couple to this object. So so that if I rotate the coordinate system, something else rotates along with it. That something else is going to be the normal to the surface, and I want it to rotate once. So I'm going to close this surface up. I'm going to have some other rotation that I'm going to couple by forcing it to stay on the same object, to have the same mathematical structure. So here's this thing. I'm going to spin it once. So I'm going to rotate this 360 degrees, and then I'm going to fold these together, and I'm going to couple them together so that one rotation of the broader structure is going to correspond to one rotation of the twist. So one rotation in twist corresponds to one rotation of the whole object. Okay, and that looks like this when you're done. Okay, so that's what I'm showing on, not that, that's what I'm showing on this animation here. So I've got one complete twist here. There's a half twist here and a half twist there. One complete twist for the whole thing. So ready, go. And that's amazing. So again, this top arrow, the blue one, is showing how this thing is rotating relative to the coordinate system, or basically how much the coordinate system is rotating relative to it. The bottom one is showing the normal. If you had this thing sticking off the side of the surface, how it would be moving around as this object rotates, or as the coordinate system rotates. So this is a one-to-one coupling. There's one complete rotation of the normal for one complete rotation of the coordinate system from the outside. Okay, so that would be, this is a spin one particle. One rotation corresponds to, one rotation of the coordinate system corresponds to one rotation of the phase. Now let's take a look at the moment you've all been waiting for, which is a spin one half particle. So this is an electron. In this case, I have my mathematical structure that corresponds to a rotation of the coordinate system. I'm going to couple it to a rotation of the phase, which is the rotation of the normal to the surface, by a factor of a half, and you get that structure. So this is like a Mobius strip. So it's got a half spin, or this, it's a spin one half. So it's got one half of a rotation corresponding to one complete traversal of the outer coordinate system. And so here we go. This is going to be amazing. So now I have to rotate the whole object twice in order to produce a single rotation of the normal to the surface. Because what's going to happen is it's going to go around the outside of the Mobius strip, and then it's going to flip over, or do it continuously in this case. It'll flip over and then trace out the inside of the Mobius strip, and then it'll flip over again and go back to the outside. And so this shows that you can have a system, you can construct a system where just because you rotate the outer coordinate system doesn't mean you're actually rotating the phase of the system. The phase of the system couples differently to the coordinate system, to the rotation of the coordinate system. And so this is a spin one half particle. Electrons, protons, all these quantum particles, well, all the fermions, all the ones that obey the Pauli exclusion principle are have spin one half, or have a half integer spin. So in this case, it's one half. I also have here a 3/2 spin. So this is one that has 3 half twists in it. I don't know of any fundamental particles that have spin 3/2, but one can imagine that it could exist. So this is one rotation of the full coordinate system on the top, and the normal sweeps around 3 times, or 1.5 times. So you get a 3/2 spin. So that is an example of a quantum mechanical system where you have the particle has 3/2 spin. You could construct a system that has 3/2 spin by combining a bunch of spin 1/2 particles so that they're all oriented in the same direction, for example. Would that work? Yeah, so that would give you, well, that would give you a total quantum number of 3/2 for the spin quantum number. I don't know if that actually implies that the mathematical nature is spin 3/2. Maybe it does. Anyways, so there you go. And then the final one is the graviton. The graviton is a spin 2 particle, which means that spin 2 particle means that you only have to go through 180 degrees in order to get back to where you started from. Okay, because if you look at this, if you have this with a spin 2, e to the I 2 theta, then that means that a rotation of 2 pi gives you 4 pi advance in the quantum phase. So you have e to the I s theta. If you advance this one by 2 pi, and if you have a spin 2 particle, then you're going through 2 times 2 pi, or 4 pi, that's a pi, 4 pi in your phase. Okay, so here we go. That's this one. And you can see that the normal to the surface goes around twice every time the surface itself goes around once. So this is an example of a spin 2 particle. A graviton is a spin 2 particle. So now this doesn't mean that this is what gravitons actually look like. And this doesn't mean, just like this one here, doesn't mean that this is what electrons actually look like. Electrons aren't little Mobius strips. What this says is their spin properties have the same structure as the Mobius strip. When you advance the coordinate system, the phase of the wave function advances at half the rate. So there you go. That is kind of some of the fundamentals of quantum mechanical spin. There are a variety of other systems that have half-integer spins. Another example that I've often used is if you have, let me pull this up this way with just the camera. So I have a pen like that, and if I rotate this, if I keep it fixed in my hand and I rotate it around, then I have to rotate twice in order to get the pen back to its original configuration. One 360-degree rotation doesn't return me to the original configuration. I have to go through 2. So there we go. That is kind of the quantum mechanics of spin. It's, like I said, it's an intrinsic property. Oh, and then something else I want to point out. So let me answer your questions, and then I'll go on to something that's interesting that's related to quantum mechanical spin. And let me do it first, and then I'll answer. Well, no, we'll answer questions first. I only took quantum mechanics a couple semesters ago, but I've already forgotten a lot of the specific math parts. Yes, that's the way things work. I've forgotten a lot of it as well. How much spin do pentaquarks have? It depends upon the orientation of the individual particles that gives you the spin of your particle. Let's see. Scalar particles are neither bosons. No, scalar particles are bosons. Because a boson, so the difference between a boson and a fermion is a boson has integer spin, a fermion has half integer spin. What that implies is that if you rotate your coordinate system, you go through a rotation of 2 pi, do you end up pointing in the same direction or in the opposite direction? That's basically what is the difference between, in this mathematical model, that's the difference between a fermion and a boson. So let me show you. So here is, let me start over. Here is a fermion. So when I go through one complete rotation, which puts me back to here, I'm pointed in the opposite direction. And so that means it's a fermion. A scalar, excuse me, which is this one, I start here, I go through one complete rotation like this, and my phase is pointed in the same direction. So that's a scalar. If I look at the graviton, I start here, I go through one complete rotation like that, and I'm pointed in the same direction. So again, that would be a boson. This one, if I go through one complete rotation, I start here, I'm pointed to the right, I go through one complete rotation, and now I'm pointed to the left. That's a fermion. Okay, now, speaking of spins, and just kind of demonstrating that spin is actually an intrinsic property, there are 2 different ways that you can magnetize something. You can magnetize, magnetization is the alignment of magnetic moments from either the spin angular momentum that's intrinsic to a given charged particle or its orbital angular momentum. So let's say that you have some atom. Here is your atom, and your electron is out here. Your electron is going to have some spin, some intrinsic spin. It's also going to have some orbital angular, or may have some orbital angular momentum. So here's its orbit right there. And it's going to have a magnetic moment. That magnetic moment can come from either the electromagnetic field coupling to the quantum mechanical spin, so that gives you a spin magnetic moment, or you can have a magnetic moment because you have orbital angular momentum like this. So this is spin angular momentum, and you'll have a magnetic moment because of spin. I don't know if this is the right notation, but we're going to use it. Or you can have an orbital angular momentum like that. So you have L, and you can have a magnetic moment that is mu L from the orbital angular momentum. Okay, so you have a charged particle that either has intrinsic spin or intrinsic angular momentum, or you have a charged particle that actually has orbital angular momentum. This one is independent of the coordinate system. This one actually depends upon the coordinate system. And you can develop a magnetic moment from either of those. It's the same charge. It's all counted in terms of h bar, right? Because h bar is the fundamental unit that everything is built upon. And so you can have, when you have a particular electron going around in some system, the amount of angular momentum that it has, or the angular magnetic moment that it has, the angular momentum magnetic moment that it has, is going to be some multiple of the spin magnetic moment that it has. Okay, the spin magnetic moment is going to be h bar over 2, basically, is the times the electron charge and a few other things. So it's going to have this half integer, and this, in this case, this is not e, this is going to be q, the electron charge. So it's going to have some magnetic moment that's related to this quantum number, the spin quantum number. The angular momentum quantum number is going to be a multiple of the spin quantum number. Maybe you have an angular momentum of 1, and so that's 2 times h bar over 2. H bar divided by 2. And so, and the electric charge is going to be the same in both cases. So the magnetic moment that you develop in one case or another are going to exactly, you can construct a system where they exactly match or where they exactly cancel. And so this is going to be an interesting thing that you can do. You can play a game with this. You can say, I'm going to build something where I have a magnetic field that points in a particular direction, but this magnetic field is going to be caused by angular momentum. So that is the orbital motion, the orbital angular momentum of the electrons going around in some system. So you have them all lined up, all the orbital angular momenta are aligned, and so I'm going to create a magnetic field that points in a specific direction. And I can also build a system where I get exactly the same result. I have some magnetic field, a north and a south pole like this, except that now instead of using a material, instead of having a material where the magnetic field comes from the orbital angular momentum, I'm going to have the magnetic field where it comes from the spin angular momentum. So the intrinsic spin of the different particles. So again, here is my system, but now it's not the orbital angular momentum that is determining the magnetic field. It is the quantum spin that's determining the magnetic moments. So it's the spin magnetic moments that are aligning. And now I'm going to make a magnetic field that's aligned in the same direction, but now it's the quantum mechanical spin and not the orbital angular momentum that's doing this. All right, so what can I do? What kind of game can I play with this? What I could do is put these two things on top of each other. I could have one disk like this and take the second disk and put it on top of this first one so that now I have two disks. So these are two disks. One of them has a magnetic field that's pointed in one direction. The other one has a magnetic field that's pointed in the opposite direction. So those magnetic fields, we can pretend that they cancel. I'll show you how you actually make them cancel in a little bit. So these two magnetic fields are going to cancel. However, this one is made with angular momentum, which is fine. So it's got some intrinsic angular momentum to it. This one is made with spins. And so this now has a spin direction. Angular momentum is not a conserved spin is an intrinsic quantum number. It's a property of the electron itself that is independent of its angular momentum around your coordinate system. And so I basically have built with this system a spin dipole. Like, here's an object that's just sitting there that actually, as far as nature is concerned, is actually spinning. It has intrinsic spin. It's a macroscopic object that has intrinsic spin, but there's no magnetic field associated with it because I canceled the magnetic field with this material. So the way that you build something like this, instead of having the two on top of each other because then things are separated, what you do is you chop it up into pieces and then you interleave the pieces with each other. Okay, so you take this system and you say, all right, here is my angular momentum magnetic field, and I'm going to break this up into a bunch of slices, pizza slices, and pretend that they all overlapped. Whoa, my thing just died. All right, so back to where we were. We have, here's this thing. It's got angular momentum. We're going to chop it up into slices. I'll do 6 because reasons. And then I have this one that's the spin pendulum. So this one has a magnetic field that is caused by the spin of the electrons and not their angular momentum. I chop these up like this, and then I replace them So I'll color these ones blue. So let's pretend that this one is blue. So I replace them so that you get something that looks like this. And then you have, that thing is blue, and then this one is blue, and then this one is blue. But you switch them. So you have them like that, you switch the orientation, and now the magnetic field from this one is going to be pointing in one direction, the magnetic field from the other one might be pointing in a different direction, but all the spins from these different slices, from the spin slices, are all pointed in the same direction. And so you cancel the magnetic field, but you preserve the spin field. And so now you've got a pendulum that has intrinsic angular momentum associated with it. That's not orbital angular momentum. It's this fundamental quantum mechanical spin angular momentum. Now, you wouldn't really do it with 6 pieces. You'd actually do it with either 8 or 10. And that is what the Etwash group at the University of Washington did. So if I go spin pendulum, University of Washington, this is what they have. So this is the artist rendition, or the computer rendition, of their spin pendulum. So they have these different pucks. They have them arranged in a particular way. You can rearrange this, the different components, so that maybe you want to have all of one magnetic field on one side and all the spin on the other side. You can interleave them. You have options. Once you make all these slices the same, you have options in how you put them together. So they have 2 different kinds of magnets. One that's where the magnetism comes from spin angular momentum, one where the magnet comes from orbital angular momentum, and then they cancel each other in various ways as they piece this together. They have a new pendulum that actually has 10-fold symmetry. That's this one. This one had 8-fold symmetry. But that's pretty cool. One of the first things they found when they plugged this thing in and they set it down in the system is that now you have an object that even when it's just stationary, so here's the Earth, here's your laboratory, you have this pendulum, it's suspended from a wire. Even though this thing is stationary, it still acts as though, even though it looks like it's stationary, it still has spin. It still is spinning, has intrinsic spin or angular momentum about a particular axis. So it's got this spin angular momentum oriented in some direction, and the Earth is rotating. So here's the Earth rotating, and you have this thing, a spinning object, that is rotating with the Earth, and whenever you take a spinning object and you rotate it, it's not going to like that, and it's going to precess relative to the spins, relative to the Earth's rotation. So you get forces acting on it because it has some intrinsic angular momentum, even though it's just sitting there as a stationary object. It still has this spin that's all the spins of the little electrons that are going around, and then that is being rotated by the Earth as the Earth spins on its axis. And what was happening is that they were seeing the Coriolis force of this object. And so the object was being deflected. It was causing a twist in the torsion pendulum that aligned it with the rotation of the Earth. That's weird. So the electrons, because of the spin of the electrons, not because of the charge of the electrons, but because of the spin of the electrons, they were aligning with the rotation of the Earth. That's pretty cool. So, and then they were looking for a variety of forces that require quantum mechanical spin to couple to the forces. They didn't see anything. If they did, they would have been even more famous than they are now. Right now, they're famous in the right circles, but they would have been enormously famous had they discovered something else. But that's the kinds of clever designs that you can do as an experimentalist, using the fact that these quantum mechanical properties are actually real properties. So there we go. That's what I've got for today.